what, so we defined this, what convergence of a series means. Convergence of a series. We understood what this thing means. Basically, you take the partial sums and you see if that sequence of partial sums converges. Let's just write it out
Yeah, so
once
just a
again.
minute.
Yeah.
So if A1, A2, A3 form is a series, A1 plus A2 plus A3 is the series which is given to us,
Mm-hmm.
and we should make sure that it's positive. Then
Hmm.
you take S1, S2, S3 as we can form a sequence with S1, S2, S3.
Right.
We know that S1 less than S2 less than S3 since A1, A2, A3 are all positive.
Mm-hmm.
So this ensures that the sequence of S1, S2, S3 is a monotonic sequence.
Right.
And we know that a monotonic sequence, if it has a monotonic sequence, this is a monotonic increasing sequence.
Mm-hmm.
If at all it has a bound,
Mm-hmm.
then limit n tends to infinity, Sn exists,
Right.
and
Yeah.
it equals to that what A1 plus A2 plus A3 so on an
By
infinity.
definition. Yeah.
Yeah,
That's right. So that's the perfect summary basically of what we did about series till now.
yeah.
Right. That's nice. So now after defining this, the definition itself doesn't let you know how would you actually decide whether a given series is convergent or not, right?
Okay.
That's the problem with this, right? This is just a definition, right? um, it just tells you check the limit of these partial sums, but how can we check this limit efficiently?
So then one more question is how do we find if there is a bound?
Yes, right. I mean, that is the only thing that basically, which that's the same question, right? How to check whether this
Yeah.
limit exists is the same question as the boundedness. So
Okay.
that's all
Okay.
basically we will try to do. We will try to develop techniques to see,
Mhm.
we'll try to develop techniques to which will help us to conclude if a series of positive terms is bounded or not, because as we realize, boundedness is the only thing we need to check, because see, we are not interested in what the series actually sums to. Okay,
Okay.
we are just interested in knowing whether it sums to something or not, right?
Okay.
So we are not interested, because rather most of the times it's impossible, right? Not interested in finding the actual sum.
So just making it clear,
Uh-huh.
limit n tends to infinity Sn. If
Hmm.
it exists, does it mean that the series converges?
Yes, that is the definition of the series being converging.
And if
Okay.
it does not exist, it does not converge.
Yeah. So basically,
Okay.
basically
Okay.
we are attempting to give meaning to this infinite summation, right? And this is the most natural choice. You take the
Okay.
partial
Okay.
sums and you let them you take more and bigger partial sums and you see if that converges or not. And that's, you
Okay.
define that to be naturally, right? So we are
Okay.
basically going to develop techniques to check if the partial sums are bounded. Techniques to check if the partial sums
Are bounded.
are bounded without
Okay.
actually finding the sum.
Yeah, I get you. Yeah. Yeah.
Yeah, right. Without actual calculation. And we will try to study the nature of the terms themselves. Okay, so our
Okay.
techniques will, okay, be based on the nature of the terms, will be based on the AIs. So we will try to study the AIs and from there try to conclude if the summation will be bounded or not.
Okay.
Okay, so oh, sorry, I think I unshared the screen. Yeah, one sec, just let me pull this up and this here. Yes. So for example, let's say that you have a abstract series A1. Let's first start with the sequence itself: A1, A2, A3, and so on and so on, and each AI is positive. Now, if it is
Okay.
given, if it's given that limit AI is equal to 1 as I tends to infinity.
Okay.
So you see, this is just an information that's given about the terms. So
Okay.
now from here, what can you say about the summation of the series?
The summation of the series.
Yeah, like what can you say about this summation?
I mean, the final answer will be less than 2.
No. Think about it. So the AIs are tending to 1.
Yeah, I mean, the last term is literally 1, kind of.
No. This doesn't mean the last. So this kind of means that after a certain point, all the terms are kind of 1, right?
Okay.
Yeah. AI becomes almost 1 as I becomes big.
Then the summation will be infinity, 1 plus 1 infinite times.
Yes, it's almost like that, right? Yeah, exactly.
Yeah.
So then the answer would be infinity. This is what, this is an example where you see we are concluding that the summation is unbounded or does not exist from just by just analyzing the terms. We didn't even have to do anything, any summation, right? We just, based on the local property of the terms themselves, we are able to say it, right?
Yeah.
So let us just write out, let's write this mathematically a bit, okay? And then we can, so this is just a very simple example of this phenomenon of
Okay.
what we are trying to do. So let's just write it out.
Okay.
So limit AI I tend to infinity equal to 1 means that given any epsilon, let's say if epsilon is equal to half, okay, then there will exist the n naught, maybe n naught equal to 100 or something, okay,
Okay.
such that a n naught would be bigger than half, would be bigger than 1 minus half and less than 1 plus half, right? Basically, we are
Yeah.
saying that after n naught, all the terms are close, are like in the half band of the half neighborhood around 1.
Okay.
Now it is clear, right? Because a n naught is bigger than 1 minus half, which is just half. So if you sum, then it's half infinitely many times, right? From a n naught. So it doesn't happen from the first term itself. It may happen from like after a
The
few
millionth
terms.
term or so. Yeah.
Yeah, right. But that's also okay for us. So I mean, I should just write k here, and k starts from n naught to infinity. So this will be, I mean, this will become, infinity times half.
Yeah.
Okay, something like that. So yeah, that's the thing.
Okay.
So now you see, this actually, we could replace the 1 by any positive number, isn't it? So
Yeah.
in here, if you replace, now we will actually get a test from here. Okay, you can
Okay.
actually replace the 1 by any positive number. If this was not 1 but 1 by 100, even then your answer will not change.
1 by 100. Okay. Okay.
Think about it. Like what
Yeah,
do you,
because
okay,
you'll be adding it infinite times.
yes, something, yeah, roughly that. So it will still be, yeah. So
Yeah. Yeah. I
so
get it. I
from
get
here we get a
it.
theorem. And so the theorem is that, so this is our theorem. So a1, a2, a3, dot, all positive, all positive if limit ai is not 0. In fact, even for negative numbers, it would be the same thing. Okay, but here I've given all positive, so yeah. But so yeah, it's not
It
0.
should just not be 0. Okay.
Yeah, right. If it's non-zero, then that implies then there's no chance of convergence, right? It implies that a1, a2, dot. This is infinite.
So if it is not convergent, can I call it divergent?
Yes, in this case, you can say so because terms are positive. So if it doesn't converge, the only reason why it will not converge is because it's going to infinity. So there's no chance of oscillations happening. So we can use the word divergent safely here.
Oh, so there's a third thing here, like convergence, divergence, and the third one.
So yeah, that really depends on the the book, because in some books they have two categories. One is convergent and one is divergent. So in
Okay.
some books they
Okay.
say that if a sequence doesn't converge, then they say it diverges. Okay.
Okay.
But in some books they say that if the sequence does not converge but goes to infinity, okay,
Okay.
means that it actually tends to a thing that is infinity, so actually tends to something, then they call it
Okay.
divergent. And if it doesn't tend to infinity also and doesn't converge also, for example, if it's 1 minus 1 1 minus 1, then there is
Oh,
a,
okay. Okay. Got
then
it.
they call this oscillating. I like this
Okay.
classification better, because otherwise, divergent, the meaning of divergent is like going away to infinity, right? Diverging. And if you are if you're putting these kind of sequences under the umbrella of divergence, then I don't like that. Okay.
Okay, sir.
But it
Okay.
depends on some books, they, yeah.
Okay.
So
Got it.
yeah, but in our situation, our case, the situation is simple because everything is positive. So it either converges or it just goes to infinity. Okay.
Okay.
So this is our theorem. Okay. Which, I mean, you could also write it in the reverse way, right? The better way to write it is that if this converges, then limit ai is equal to 0.
The vice versa is true.
It's
Whole.
no, this is not vice versa. This is the same statement. This is
Oh,
not the
okay. Okay.
converse, right? Think about it, right? Yeah, it's the same statement, right? So if it converges and if the limit was not 0, then it would diverge.
Okay. Okay.
Right.
Got
So
it.
it's the same. This is the contrapositive, right? So, but you
Okay.
just think
Okay.
about it intuitively, it's the same thing. So yeah,
Okay. Okay.
I was actually going to come to the converse. Is the
Okay.
converse true? Is there a sequence where the limit is 0? So now let me write the converse first. Okay. So
Okay.
I mean, the converse may not be true, but at this point it's just a question mark.
Okay.
If limit ai is 0, which means basically means the terms become small,
Limit is
then
0. Okay.
is this going to be convergent? That is our question. So the terms are becoming smaller and smaller. Does that imply though that this converges? So this is a question mark. This is not a claim.
Yeah. Yeah, okay. Uh, yeah, I feel it so. Yeah, it converges.
Okay. Okay, yeah. But in fact, this is not true.
Yeah.
Yes, yeah. I mean, but yeah, it's not intuitively clear. Okay,
Okay.
but in fact, this is not true.
Okay.
Uh, let's try to. So the easiest example that I can think of, in which is even there in the notes, is not easy. Okay,
Okay.
so but we will show it. So let's
Okay.
see. So basically, see, the idea is that even though it is going to 0, it might be taking a very long time to go to 0. You
Okay.
see,
Okay.
that is the problem. So let's see. So something, I mean, so you could have something like this, for example. Yeah, this is actually a very simple example. So you just take many copies of the term. So you're taking one, then so let's say you start with this sequence. Okay, you know that this goes. Obviously, when you're trying to construct a counter example, you would start with a sequence that does go to 0 and somehow make a series from there which does not converge,
Okay.
right? So I start with, this is just an experiment. I've never done this before. I'm just trying it because it's not a typical
Okay.
example. Now you see this
Okay.
one. Now what I can do is I can repeat the terms, right? I can take the half 2 times. I can take the 1 by 3 3 times.
Okay.
Okay. And so on. I can take the 1 by 4
Four
4
times. Yeah.
times. Yeah. Now you see clearly, if you look at this sequence, the terms are still going to 0.
Yes.
The terms are still going to 0, but they're taking a very long time to do that.
Yes. Yes. Yes.
Yeah. And clearly this is not convergent, right? Because you think about it, right? This is 1 and this is 1 and this is 1 and this is 1.
Oh, yeah, yeah, it will go to infinity. Okay, okay.
Yeah, so this is something that I just created on the spot, okay? Because you usually I do never give. Usually I just start with the example of a more harder series, and we prove it by
Okay,
some technique. But this is a very simple example that anyone can just create, kind of like that, right?
okay,
So
okay.
yeah, basically I have taken a sequence that goes to zero, but then I just took many copies of it just to make the rate so slow that yeah. So basically, the what we understand from here is that just converging to something zero or something is not enough. The rate at which something converges is also very important.
Plays a big factor. Okay,
Yes.
yeah.
However, that comes like in the later courses. Okay. So this will not be touched upon in this course. The rate of convergence though is very important. So yeah.
Okay.
Anyways, now let us come to a more interesting sequence, right? Because basically what I gave you is I just said this diverges, right? So yeah, right. I just said that this diverges and I just broke it up somehow. So this is not a very interesting example, right? I need to give a